Welcome to our session today. My name is Katie and with me we have Shona from the Education Centre at Geoscience Australia. So our first thing we'd like to do is the acknowledgement of countries. We'd like to acknowledge the traditional owners of all the lands on which we meet virtually today. I think mostly that's ACT. And pay our respects to their elders past and present. We'd also like to extend that respect to any Aboriginal or Torres Strait Islander people who are joining us for today's session. So today's session is titled Learning Resources for Teaching Upper Primary Earth Science, so focusing on Year 5 and 6, Stage 3. Now, it is a small group today, so we're happy for you to ask questions as we go through. You're welcome to either unmute yourself and ask verbally if you're happy with that with the recording, or you can type it in the chat box and we'll try and keep an eye on the chat. We're aiming to present for about 45 minutes and have about 15 minutes at the end for questions as well. A lot of the things we'll be talking about today are activities that you can do with students. So we'll give you some background information so you have the knowledge to teach, but we'll also show you some activities that you can use in the classroom, hopefully using easy to find equipment that's accessible in a school setting. So, Geoscience Australia. Geoscience Australia is the National Geological Survey, and we provide geological and geographic information for the nation. And the education team at Geoscience Australia is quite small, but we do have a variety of things that we do. Our main focus is education delivery, and in normal times, this would be physical visits to the education centre. So we have visits from local ACT school students, but we also have visits from interstate school students coming to Canberra on the Visit Canberra tour, the civics and citizenship sessions. All of our hands-on visits to the Education Centre are curriculum linked, so we go from Year 4 up to senior school. We also produce education resources, less physical resources, more online resources at the moment. So what we've been focusing on in the last few months with COVID has been creating videos, particularly videos that show what you can't see by not visiting Geoscience Australia. So tours of different places that students might come to if they did visit us. We've also been working on student activities that can just be picked up and taken into the classroom and run with your students. We also do teacher professional development sessions like we're doing today. Mostly they're on-site sessions, but we have been branching out into the virtual sessions over the last few months. And we do some education outreach as well. Now, I'll just go through some of the curriculum links so you know where we're coming from. So we're focusing on the Australian curriculum Year 6 Earth and Space Science, and the science understanding is sudden geological changes and extreme weather events can affect Earth's surface. And we're particularly focusing on those sudden geological changes. And we wanted to point out that these are fast changes. So if you attended last week's session, we were talking in Year 4 about slow changes to the Earth's surface. This, in contrast, is fast changes to the Earth's surface. We've noted up the elaborations there as well, and we will provide this PowerPoint to you either later this afternoon or first thing tomorrow. So these are all, will all be there, and all of the links of things that we show you'll be able to access after the session. Now, there are a few of the Science as a Human Endeavour strand notes that relate to this topic. We're not going to go through all of them, but we particularly wanted to point out this one here, which is exploring institutions and locations where contemporary Australian scientists conduct research on catastrophic natural events. And that is Geoscience Australia. So one of the case studies you might want to use for that human endeavour elaboration might be Geoscience Australia, and there's some resources that we'll show you today that links to that one. There are some more Science as a Human Endeavour dot points that relate to this natural hazards topic as well. I'm now going to hand over to Shona to just start talking about how you might develop this topic in the classroom and what activities you might use.
Thanks, Katie. So in the tuning in stage, this topic, whatever you might call it, has great potential for something dramatic at the start if you wish to. You could be very gentle. You might have tie-ins and links to a novel that you're reading with your class as well. You might create some sort of great imaginative situation where they imagine a situation after a particular natural type of hazard has occurred. You could take that further and literally make your room look like the hazard has occurred, trash your classroom, and surprise your students on the first morning back at school or whenever it might be. That would have a big impact, I think. You might focus on immediately working out drills, imagining you're a Japanese school teacher working about what to do for an earthquake drill. Or you might also do something like a holiday task where you get students to monitor earthquakes, and we'll show you a site that's really good for that in the preceding week and see how much is going on around the world. Now, obviously, a topic about rapid change, natural hazards and disasters is potentially delicate depending on where you are within the country after the summer of the previous summer. So, you know, caveat in all of this is being thoughtful about that. It could be that rather than doing bushfires, it's a good idea to potentially do something about earthquakes, because that's not something that the students themselves may have experienced. So on the next slide, Katie, what is a hazard versus a disaster? This is something you do need to tackle. I come across a lot of teachers who are calling their unit natural disasters, and I would actually urge you not to do that, because it's really about the fast changes to the surface caused by various hazards. And the hazards could be, you know, things like earthquakes and cyclones, and they might have a negative effect. They might have a big impact or a smaller impact, but it's only disastrous if the impact is major loss of life, you know, or any loss of life, loss of property, and the community not being able to cope with that and having to get external help to recover. That's when it becomes a disaster. And in the way that we're talking about disasters, it's not always one person's disaster, and maybe focusing with the students for a while about what might be an individual disaster is not what we're going to classify a disaster for the purposes of this unit. Now, on the next slide, we're actually going to introduce something that comes up when I teach older students, but this is where we're talking to you as the teachers, not the students, and letting you into more background. Now, I used to teach about this often in high schools, but did not know about this risk triangle approach. But it's the way that people here at Geoscience Australia who work with our community safety branch tend to think about things and hopefully quantify things, not just in a qualitative way. So thinking about risk involves these three things. First of all, understanding the hazard, understanding its scale, its frequency, the locations where it happens. So fully understanding the hazard, cataloguing the history of that hazard of whatever type it might be. The second factor is what is exposed to that hazard. So what buildings are potentially in the path of a cyclone? What businesses might they be in there? Are they residential? Is it businesses? What infrastructure, electricity power lines, gas pipelines, roads, rail, all of those infrastructure. And then of course, what people are exposed. How many people are in a particular area? All of these things are spatial types of information, and Geoscience Australia holds a database called Nexus, which holds a lot of this information, but also the government has lots of other ways of getting that information, such as the Bureau of Statistics information about people. The third factor to take into consideration is the vulnerability of those exposed things and people. So let's take the example of a 3-story block of units. You can have a 3-story block of units which is really robustly built and is not very vulnerable. And you can have one that's built terribly and is much more vulnerable to the same hazard. Or you can have a population of people who are mostly fit and well and able-bodied. Or you can have a very large proportion of elderly or infirm people within a population, and they are a more vulnerable population. And of course, in general, this shows up the divide between your more developed and less developed countries. So that's the idea of a risk triangle, and we'll come back to the words hazard, exposure and vulnerability a couple of times later on as well. Now, when we get an upper primary group come to visit us on site for this topic, we start off actually categorizing different sorts of hazards. We actually go flashcards and we categorize into two groups, either our meteorological, atmospheric climate hazards, or our geohazards, the hazards that happen on the ground. So we have these classifications here. It's a great way we have a conversation and find out what the students might already know about. Do they know which was the worst landslide in terms of death toll in the country? Most of these things are further back than their memories will be. Explaining what subsidence is, that's about sinkholes, particularly in limestone areas. But for the purposes of Australia, then asking, well, which of these groups of hazards is the dominant type in our country, and then get them to think about, well, which of these groups of hazards is more likely or equally likely in our neighbouring countries like New Zealand, Papua New Guinea and Indonesia. And that gets us thinking beyond just Australia. It is a very long list of hazards, so please give yourselves permission to not try to do them all. It's too much. You've also got cross links with geography curriculum where the atmospheric hazards come up perhaps in year 5 there. So make sure you're checking and coordinating across that, but don't try to do everything. So our suggestion, being Geoscience Australia, would be have a go at focusing on your geohazards. And we are not even really getting to the tsunami part today. That's a whole nother potential discussion. So I'm going to hand back to Katie, who's going to talk about introducing maps and earthquakes and that sort of thing.
Thank you, Shona. So Shona mentioned in the introduction that tuning in idea of maybe getting students to monitor earthquakes. And this is the website that we use to monitor earthquakes around the globe. This is obviously my PowerPoint, but I'm just going to share it in a web browser so you can see it a bit bigger. So this is the IRIS jumbo seismic monitor. And the first thing that we would talk about with students is that this is a map, and every map has a key or a legend, and that key or legend helps us interpret the map. And the key is up in the corner here. So the color of the circle represents the age of the earthquake, of the event, and the size of the circle represents the magnitude or the size of that event. So you can see earthquakes plotted on this map. And some of the questions you might ask your students is, are the earthquakes evenly distributed across the globe, or are they occurring in particular locations? Which is the biggest earthquake that's happened today? Now, when you have this on a computer screen that you can interact with, you can actually highlight those circles, and it won't work for me because I'm in the jumbo version, but you can highlight these circles and it will bring up more details on that particular earthquake, the location and the size. You might want to talk about, oh, sorry.
I was just going to say, the thing that surprises the students most of all is how many happen.
Yeah,
every day, magnitude 4 and bigger, and we're often talking 10 to 20 every day.
Yeah,
and then
so
they go, I didn't hear about that on the news. No.
That would be a really great thing, just to count up how many earthquakes have happened today and count that up over a week, and see that average number of earthquakes per day. And look at Australia. Has Australia had any recent earthquakes? Today, no earthquakes in the past 2 weeks, but as Shona just mentioned, this website is only showing earthquakes of magnitude 4 and larger. If we wanted to look at Australia in more detail, we might go to another website, which is the Earthquakes at GA website, and this is linked in the PowerPoint. This focuses in on Australia, and so you can highlight particular earthquakes in particular locations. It can bring up those details. If you just want to look at all of the most recent earthquakes, you can click recent earthquakes and it will give you a list there. But this was also plotting those smaller ones that don't show up in this IRIS seismic monitor. Now, a really great activity you can do with students if you have an interactive whiteboard is to actually annotate the map or draw on the map. So you can get your pen and you can ask them to join the dots. Oh, I'm not very good at drawing on a computer screen, but hopefully I should have changed the color. Hopefully you can, I don't know how to do that. Hopefully you can see there that I'm drawing a blue line that's joining these dots. And if you get the students to join all of the dots, and you might ask them, what have you just drawn? What am I drawing here? And hopefully some of them will know that you're actually drawing the edge of the tectonic plates. So that's a really great way to start thinking about why earthquakes happen in particular locations. So when this movie starts, it's going to show a map of the world, and it's going to use those same circles to represent earthquakes. The size of the circle represents the magnitude of the earthquake. When the earthquake pops up on the map, it'll make a bop sound, and then it will disappear down to a little spot. We're not going to watch the whole thing. We're only going to watch until about March. There's a few other things that I'll mention. In the bottom left corner of the map, it will scroll through the date. So this is by date through the year. And then there'll be a yellow line which comes across the whole map, which is a cumulative graph of the number of earthquakes. So I'll get it started, and we'll just watch for a little while. Let me know in the chat if it's too loud for you.
Seems all right to me. So it's magnitude 7s and larger that get listed individually.
So again, we might ask the students, are the earthquakes occurring randomly? Are they evenly distributed? Where are they mostly happening? How's Australia going in terms of earthquakes? Focus in on New Zealand.
Usually with a group of students, they're all jumping and talking to each other at that point. Such a surprise, and we play it again.
So, as I said, I know 2011 is a while ago, but there were 2 significant earthquakes in that particular year. There was earlier on in February, there was the Christchurch earthquake in New Zealand that I'm hoping a lot of you know about. And then there was obviously this event in Japan, so the Japanese earthquake magnitude 9. Now I'm just going to scroll through to the end of the year and have a look again. So there's a few things you might want to look at with students now. So you might want to look at this cumulative graph. This point here on the graph is the Japanese earthquake. That jump up in the number of earthquakes is aftershocks specifically associated with the Japanese earthquake. And then you can see it goes back to being quite a steady line. If I get the timing right and go to the end of December, we're talking about 9,000 earthquakes of magnitude 4 and larger a year. So a huge number of earthquakes in a year. But again, you can look at Australia and see not very many. Again, draw the dots, join the dots, see the earthquakes around the edges of the tectonic plates here. I'm going to go back to our PowerPoint because we have 2 more resources that GA has produced that can support you in teaching this topic. So the first one is the tectonic plates jigsaw puzzle, which shown as holding up now. This is an A3 download that you can get off our website. You can get the students to cut out those particular pieces of plate that's shown as holding up now and join them together. So this is a really good one to get them realizing that a tectonic plate is not just underneath the land, underneath the continent. They also include ocean. as well. And it's the right size to be stuck into a book. We've also got this activity based on a tennis ball. So back to thinking about map projections. So you can cut out the tectonic plates in a sphere and stick them on the ball and see how they fit together in a 3D type globe.
So you get a need to get one made up again. You have a world map, but that world map also includes the plate boundaries, and they can see it properly projected.
Yeah, we also have this on a basketball as well, which is available on our website if you wanted to go bigger. Now, the main thing that we want students to take away from these videos, these activities, is that the Earth is very active. It's not sitting still doing nothing. Things are happening all the time. We just don't always hear them on the news. We don't hear about them if they're happening, particularly in other countries. I'm going to hand over to Shona now to show you a few activities you might want to do with your students about earthquakes.
Okay, so understanding earthquakes. The most common thing people think about earthquakes is like a number. What's the size of the earthquake? And you go, oh, it's a, you know, it was a 6 or it was a 7 or something like that. So that number refers to the earthquake's magnitude. And you've probably come across the idea that there's a couple of different scales. There's an intensity scale for earthquakes, which is about the impact that is felt and experienced of an earthquake, but that's not usually reported on as the main thing in the news. That's the magnitude, and the magnitude refers to the amount of energy released by an earthquake. Now, there are various algorithms used to work out the magnitude, and you have probably all heard of the Richter scale, and we've put a cross over it because it's actually not the scale that our scientists use, and it's not the generally used international scale for earthquakes. The moment magnitude scale, moment magnitude is what is used. But I think the safest thing to do is just not refer to the scale on a day-to-day basis, just say it is a magnitude 6 or a magnitude 7, something like that. Now, the way the scale works is a bit weird. In terms of energy, if you multiply by 30, well, technically 32, but let's say 30, then you are representing the change from, say, a 5 to a 6, going up one number. So you can see if you did something with your students about times by 30, times by 30 again, times by 30 again, the number rapidly gets very much larger, which is how the magnitude scale works. So the difference between a 6 and a 7 earthquake in terms of energy is a very significant difference. Now, there's an activity that helps to illustrate this, and it's called spaghetti quakes. There's a sheet that we have that you can download. Katie will have a reference for that. But just to illustrate the idea, in this activity, you get hold of some spaghetti, and this strand of spaghetti and the energy I have to put into breaking it is representative, say, of a magnitude 5. So I break that, magnitude 5. But then times by 30, and I've got a bundle of 30 pieces of spaghetti here, and breaking this is representative of a magnitude 6. And I'm going to carefully do this, and I can break that easily. I didn't make a mess, great. Now, times 30 again, you end up with needing a much, much larger bundle. And here's a representation of the bundle here, and we're up to representing a magnitude 7. Now, this is all wrapped up, but what an opportunity this offers. For the kid that you are really sick of, get them out the front and break that, matey, try as best as they can, and they are not going to break this. And they're getting the idea that, oh wow, that's really a lot bigger than the previous. Then think about the cross section at the end here. The area of that cross section, remember this is comparable to a magnitude 7, excuse me. Then there's cut up pieces of paper. A diameter of that size would be a magnitude 8. And then when you get to thinking about a magnitude 9, I've got to step back here. This would be the diameter, or this would be the size of the piece of paper you need to represent the end of the spaghetti bundle. So that's a big, big change. Now, that's a great, probably a good way to do a demo or just a slightly guided demonstration about magnitudes. But an alternative is the good old YouTube video, and there's quite a nice one that Katie's haven't got an image for here, where it just keeps on scaling, so that they add a new circle on the outside and the inner circles shrink down, because the new circle on the outside is always a bigger magnitude and it's way bigger. And there are examples being shown there as well. Now, we won't show that for the point of view of time at the moment, but that's a good resource too. Now, staying on the topic of magnitudes, many of you will have resources that were written pre-2016, and if they're referring to the size of particular earthquakes in Australia, they may have inaccurate numbers on them. So there was an international effort to check the calculations and recalculate the magnitudes of earthquakes around the world, particularly 6s and larger. And that had an impact on what Australia thought of as its top 10. So prior to these recalculations, the Mebri earthquake in WA that happened in 1941 was calculated at a 7.2, a really significant large earthquake. It was a large earthquake, but after the calculations, it had its Pluto moment. It was demoted and it came down to 6.3. So if you're talking about the largest earthquake that we accurately know about in Australia, of course, we've only got about 100 years of accurate measurements. That happened in Tennant Creek in 1988, 6.6. And in fact, there were 3 earthquakes of magnitude 6 in one day, and they're all on this top 10 list. And that's pretty significant. Tennant Creek was not known as a place that was highly active. So, you know, it's a real example of something could just start to happen, even though we didn't know it was going to be coming and there wasn't much activity there beforehand. So bearing in mind, we've got these changing calculations, but of course, then the story gets murkier, because last year, July, there was a 6.6, so an equivalent magnitude, and it happened just off the coast of West Australia as part of the Northwest Shelf, so in the shallow marine. It happened within the continental crust, but technically it's a marine zone. So that's an equal largest earthquake that we've experienced in Australia, but it may not be in the list of Australian earthquakes because it's not part of the land. Now, Australian earthquakes and the responsibility for monitoring earthquakes in Australia falls to Geoscience Australia. We have a network of seismometers around the country. There is a monitoring base here. We have seismometers feeding information. We got seismologists, as humans, talking to that. And we just produced a video earlier this year which brings that all together. Katie's just going to play just a little beginning of that so you can see what that might entail, but I think it will be useful.
Yep, so again, I've put this in the chat, so if you have issues with sound, just watch the first 20 seconds of it. But here it is. Oh, I don't think I pressed the sound button. Yep, okay, sharing computer sound. Let's play.
Hi, I'm Shona from the education team at Geoscience Australia. Have you ever felt an earthquake? Today we're going to find out about earthquake detection and monitoring at the National Earthquake Alert Centre here in Canberra. I have with me Steve. He's one of the seismologists that work here. That's an earthquake scientist, and he's part of the team that's on duty here every day of the year.
Right. Always horrible to watch yourself, but it goes on to be quite useful. And that's a plug for our playlist of various videos on YouTube, because there's also another one about earthquake monitoring, looking at the seismographs that we have recordings from as well. Now, when Katie gets the PowerPoint back, a couple of other resources that we have available online. This poster, it's not one that's in print, but it's still available online, is a really good way for looking at the pattern of earthquakes within Australia, because it looks at 1 year's worth of information. That's all the red circles, and they're proportional circles according to magnitude. And then the yellow circles are the previous 10 years worth of recordings. So even within Australia, we don't have an even distribution of earthquake occurrences. We often talk to students about the fact that there's 3 main high concentration zones. We've got the north of Adelaide, the Flinders Ranges. That's a definite zone of crumpling of the crust, because the crust is actually being squashed there, so they get more activity. The whole of the southeast corner of the country, including Canberra, but also southern New South Wales and Victoria, that's a more active zone. Look at Queensland. It's really quiet in comparison. They've had a few things offshore in recent years, but it's not a very busy place for earthquakes. And of course, in West Australia, that southwest corner is also pretty active as well, but also dotting up through the country too, or through the coast there. And then the next slide, Oh, no, that's a point, Katie. That graph I really like because it actually shows the number of earthquakes of different magnitudes in that 1 year. The longest bar on that graph is for magnitude 2s. So there's heaps and heaps of magnitude 2s happening, hundreds of them, much fewer for the higher magnitudes, and rapidly drops off. And you'll see the bar for magnitude 1s is shorter, and you might go, well, what's going on there? We actually do probably have more 1s than 2s, but we don't have enough instruments in the network to pick up these very low energy earthquakes that only radiate energy a relatively short distance, so they may not get picked up by our instrument system. Now the next slide shows earthquakes that are our largest in the recent decades, and the very largest are shown in those red circles, sometimes covered over by other colors of circles. I think it's really interesting to see that the pattern here is not very clear, and it doesn't replicate the places which have frequent earthquakes. The Flinders Ranges hasn't had a ginormous earthquake, even though we get lots of activity there. Same for the southeast. But southwest has. Meebury happened there. Then you have Tennant Creek in the middle of the Northern Territory. We have the earthquake in the Peterson Ranges from 2016, which was a 6.1, so significant, but very remote. And then we've got the activity up sort of beyond Broome. So you get left with the, where next if we ever get another big one. Very difficult to predict, very, very difficult to predict. If you want to get your students to research earthquakes in Australia, then we have a story map. So this is a map with information associated with the dots about earthquakes of significance that have happened during the last, well, more than 100 years, in fact. This is where you can find out some stuff about the Newcastle quake from 30 plus years ago, noting that Newcastle, which people all know about, was only a 5.4 in magnitude. So magnitude is not the only issue, that's the hazard, it's what was exposed at that point, what was the local conditions. Now, what was exposed can also be dealt with in terms of a little activity. Now, I'm going to swap over. Let's show this first. So this is looking at when an earthquake has happened in Japan, and we're just going to play maybe a minute of this video as well. So this is during the earthquake in Japan in 2011, and this is in Tokyo, I believe. And I think it might surprise students to see this. Can you see the top of that building? There's something swaying as the building sways as well. And then watching these two enormous buildings literally sway because of the earthquake that has happened. And I think they keep doing this for quite a long time after any actual earthquake shaking has finished. So this video goes on to show some other images from, I think it's Tokyo as well, particularly water coming up out of the ground. So there's liquefaction, water coming up out of the ground, and literally the ground moving, and cracks that are sort of expanding and contracting. So there's nothing nasty in that video, but well worth looking at. But let's just focus on buildings. And this is a little set of equipment that goes with an activity. It's not one that we've written up, but this is from a place or a site called Earth Learning Idea, and they've got a little write-up of this. And it's an idea of looking at building heights and what happens when the ground shakes. So the equipment, and my equipment is malfunctioning. So what you should have is a piece of wood which has got holes in it that perhaps fit some little bits of dowel. And you have different lengths. You have a tall, a medium, and a short piece. And in our case, we've popped some blue tack on the top for some weighting. There's a different version where you might have cardboard with bulldog clips at the top to provide some weighting. I've gone today with blue tack, and it's not completely cooperative, but I hope I'll be able to give you the idea.
Too melty, too hot today.
Too warm today. So I've got this on my table here, and we're looking to see what happens if we shake it. So I'm going to shake this slowly at first. And I hope you can see that the tall building that we're representing is shaking. It's moving. If I shake a bit faster, perhaps at the angle I can see the middle one is actually reacting more now. The tall one's a little less. And if I shake really quickly, and this is a bit dodgy, you should be able to see that the small one can sway with a different frequency of shock waves coming through it. So this is to do with something called the building sort of resonance, and understanding your hazard in the place in question leads to having building codes and building structures which are going to be more resistant and able to cope with earthquakes. Of course, the main thing is that these buildings do flex rather than be brittle and break. So that's a little activity there. What's next?
That's me.
It's Katie.
I'll just share my screen again. Okay. Are we sharing the right screen?
Yes, you are.
Okay, so if we stop thinking about earthquake hazard and start thinking about volcanic hazard, there's a number of factors that we can look at. So that hazard factor is mainly to do with the type of volcano that we're looking at, and the kind of eruption it produces. So not all volcanoes produce the same kind of lava, not all volcanoes produce the same kind of eruptions. So we have an activity that you can run with your students about understanding viscosity and volcanoes, using cornflower slime as a model for lava. So if you're looking at the photo here, you need cornflower, food colouring and water. And you make up 3 different mixtures of cornflower slime with different amounts of water. Now, I am going to preface this by saying this is an activity you need to test in your situation beforehand, because the climate and the humidity can impact the viscosity and how runny that cornflower slime is. So we've given some examples for Canberra's situation, but in other locations and potentially at other times during the year, you might need to change the amounts of water that you're adding to make these cornflower slime mixtures. So the idea of the setup is that you would have a clipboard, which is showing there, clipboard with a labelled piece of paper in it that sits down into the top of a photocopy paper box. Now, photocopy paper boxes make that really nice slope. It can be consistent throughout the groups across the classroom, but there is a factor you need to take into account, which is photocopy paper boxes have these little holes in the corners, and particularly these corners down here, the slime does leak out. So it's best if you masking tape up those holes before you do this activity, just to reduce the mess a little bit. Hopefully these are easy resources that you can get at school. You can collect them over time. So I'm now going to share a video of this activity. And I'll talk through, there's no audio for this one, so I'll talk through how this one works.
Set, go.
So I'm the videographer in this situation, and I counted down. I said 3, 2, 1, go, or something similar. My helpers tipped that lava slime at the top of the slope at the same time, and you can see how it ran down the slope at varying speeds depending on the viscosity of that lava. You can see Shona there holding the very sticky lava. It's still running down a little bit. Now, there are lots of great things you can do integrating maths into this. So if you videoed it, you can do slow-mo video, calculate the speed of those different viscosities of lava. You can collate that information as a class, do some graphing activities. So lots of potential for further extension activities as well. I mentioned at the beginning that the viscosity of lava relates to the type of volcano that's produced. And so we have 2 different volcano cutout models that you can download from our website. Shield volcanoes here are related to that very low viscosity lava. And stratovolcanoes are related to high viscosity lava. Now, one thing I should have mentioned in watching the video is that lava viscosity is not impacted by the amount of water. So cornflour slime viscosity was to do with the amount of water we added. Lava, the viscosity is to do with the silica content of that lava. If you download that activity, it goes through all the details of that in the activity. There are some other great things in that activity as well to do with looking at real volcanoes around the world. So we've got some links to Google Earth tours that show different cones, different shapes of volcanoes around the world. A similar activity that's more hypothetical is from our landslides booklet, which is another type of hazard that you could focus on. So using some maths again, could you outrun a landslide? So we get the students to work out how fast they can run and then calculate if they could outrun a landslide. There's a few different scenarios as well. So a scenario, could you outrun a laha, which is a volcanic mud flow type of landslide? And there's another scenario in that booklet as well. And the links for these booklets and the activities are all in the PowerPoint as well.
Just to let people know, our booklets have answers to the activities usually.
Yes. I think the first activity in this is based on how fast the students can actually run, but then the other ones are standard numbers. So that would be easy to check the answers for. If you're wanting to do more of a role play activity and think more about volcanoes, our volcano booklet, which Shona's holding up, has a great activity called Thunder Island Role Play. And this is about a hypothetical volcanic island that students work in groups to monitor a volcano on that island over 6 hours. So every hour they monitor it. It's got some great mapping activities. They're looking at the seismicity, which, so earthquakes that can predict volcanic eruptions, deformation of the earthquakes, water, groundwater changes, weather changes, and the potential for an eruption. So that's a good one to get students working together, thinking through scenarios, those kinds of things. And that's a lot of what I guess Geoscience Australia emergency management does, thinking through scenarios and what might happen in different situations. Now we've got one more activity that we'll mention that brings all of these things from the risk triangle together. So understanding hazard, exposure and vulnerability is all brought together in this activity that we've titled Think Like an Emergency Manager. Now, this was actually written for high school students, but we don't see any reason you couldn't use it as an extension with upper primary school students. It asks them to look at a hypothetical case study of an Indonesian volcano and the exposure and vulnerability of local towns, and work out what an emergency manager would do in different situations. So across the year, there are different climate things, there's different weather patterns, and those would change where, say, ashfall goes, or how the pyroclastic flows might move, and all of those are activities that the students work through to think about, okay, if this happened at this time of year, which towns might be affected, what do we need to do, where's the water, where's the food, where's the infrastructure, what's going to be impacted. This is supported by a PowerPoint presentation. So this is a slide from the PowerPoint presentation that goes through those hazards. So talks about volcanic hazard, talks about lahars, talks about pyroclastic flows, talks about ashfall, and then has the mapping activity as well. So again, a really good geographical activity using those mapping skills. Moving on from that, we're just going to think about vulnerability for a minute, because understanding vulnerability is a difficult thing sometimes, and reducing vulnerability. How do you change the vulnerability of a population? And one of the things that you could do is community education. So if people know what to do in certain situations, they're less vulnerable to being negatively impacted by those situations. If people know when there's a tsunami, they need to get off the beach, then we reduce that vulnerability in that population. So as a part of a side project that GA was doing in Papua New Guinea, there was some community education resources produced for earthquakes, volcanoes and tsunamis. And Shona's holding up the booklets now. So there was booklets, there was posters, and there was a little animation as well on tsunamis. Now these were specifically written for the communities that they were educating at the time. They were written in local language as well as English. So these resources are really good from 2 points of view. They can be discussed with your students as educational resources. This is what to do in an earthquake. This is what to do in a tsunami. They can also be examined as an example of reducing vulnerability. This is how we can support vulnerable populations. This is how we can support developing nations to reduce that vulnerability to the hazards that they can't get rid of. They can't stop earthquakes, they can't stop volcanoes, they can't stop tsunamis, but with knowledge and information, they can reduce the risk of those things negatively impacting on their people. There are a few other resources that we'll just mention as well. I know we're nearing 5 o'clock. So all of our resources we've mentioned are available online, ga.gov.au/education. The easiest thing to do if you know what you're looking for is to click on the tiles that are the type of resource. So you've got the videos, we've got student activities, we've got online resources, those kinds of things. If you don't exactly know what you're looking for and you just want to know what's out there, you can click on the resources search tile and it will bring up this web page here. It's a filterable list of all our resources. So you can filter by subject, science or geography, by year level, that's Australian curriculum year level, by topic, so you might look at natural hazards, or by resource. If you know you particularly need a poster to fill an empty space on your wall, you could filter by the posters there and get what you need. We also have a number of other geohazard resources. This isn't particularly to look through now, but these links will be here for when I send out the poster, the PowerPoint at the end. So there's some more videos, some of those teacher booklets we mentioned. We also have a Minecraft video. Maybe year 5, 6 students are a little old for Minecraft, but if not, we have some Minecraft posters and we've recently brought out a video to accompany those posters. There are also some great online resources that aren't produced necessarily by Geoscience Australia that we like to recommend. Firstly, I'll mention Earth Learning Idea down the bottom here. So Shona showed one of those Earth Learning Idea activities, the Building Resonance one. Earth Learning Idea is a UK website. It's not pretty, but it has great resources on it. So it has these double-sided activities that have background information, that have images and photographs, and then have how to run the activity, how long it will take, what resources you need, what kinds of questions you should be asking your students, and what metacognitive thinking might be promoted in students by doing this activity. Tsunami, the Ultimate Guide, is an amazing website of everything tsunami. If you need something tsunami, go here. So it has tsunami basics, it has science behind tsunamis, it has information about warning systems, it has great videos that you can access as well. So heaps and heaps of information in there. And that was produced by Surf Lifesaving Australia. So they recognise that even though we don't get a lot of tsunamis in Australia that impact the land, we still get tsunamis that do impact the water and the rips and the currents, and people should know about those kinds of things. Stop Disasters is a nice bringing together game that wraps all of these things up, that risk triangle thing again. So it's a interactive computer game for students. They build a city or a town and they try and avoid being hit by particular natural hazards and disasters. So that might be a good one for the end of the unit to bring all those thoughts together. So that is the end of our presentation today.